Good afternoon. So now we'll start the interactive live session on week 8 videos. So first of all, I'll go through the recap of week 8. So in week 8 videos, we had 2D DCT, Walsh-Hadamard transform, then data dependent transform KLT, and singular value decomposition SVD. So this week's lectures were all mainly on the concept of data dependent transform KLT. Most of the portions deal with the KLT transform. So we can go through this 1D DCT. So 1D DCT introduces implicit periodicity by symmetric extension. So the question 1 is, in figure A and B, which is the periodicity assumed by DCT? So which one is the implicit periodicity? DCT introduces implicit periodicity by symmetric extension. So in DCT doesn't do any explicit modeling of periodicity, but it automatically comes like the data samples are periodically extended in a symmetric form. So which one in figures A and B, which is the periodicity assumed by DCT? The answer is B, since A has sudden jump from a higher to a lower thing is there, but in DCT, so from equation sir has derived that there is a symmetric extension, periodic symmetric extension, so there is no sudden jump from high to low values. So here we can say that, so this is the reason for why DCT is more energy efficient. So most of the coefficient values will be focused on the low frequencies only. Then comes diagonalization property of DCT. Here we know the DCT matrix C for a particular order n equal to 2, n equal to 3, etc. So if we have a symmetric tridiagonal structure matrix, if you have a symmetric tridiagonal structure matrix like this, then if you use C, so here it is 4 by 4, right? So if you use a C of size 4 by 4 and apply CB, this is B, this matrix is B, this tridiagonal structure matrix is B, and if you are doing CBC transpose, then that will be purely diagonalized. So that matrix will be purely diagonal. So if we have a symmetric tridiagonal structure, that will be purely diagonalized. And in the case of Markov 1 processes, normally the covariance matrix will be looking like this. Like we'll have 1 for the diagonal elements, and for the other values it will be decreasing, like 1 row square, etc. And it can be shown that if you are doing beta square R inverse, then that will be like looking like this. So we can say that if rho tends to 1, this beta square R inverse becomes a tridiagonal structure. If rho tends to 1, this becomes 1 by 1 minus alpha minus alpha. Here also it becomes 1 minus alpha, right? So this matrix beta square R inverse will become a tridiagonal structure, and for such a tridiagonal structure, that discrete cosine transform matrix will fully diagonalize. So this thing is there in the assignment. Then how can we find a 2D DCT from a 1D DCT matrix? We have a DCT, we have some equation for DCT, no? That was there in the last week. So we have this C for say n equal to 2 by 2. We have a C matrix, but this is for one dimensional case. But if you want to find out a 2D DCT using 1D DCT, the simpler thing is like this. We can write a script C. So if you have an image like this, a 2 by 2 image like this, if you have C matrix like this, a 2 by 2, this is a 1D DCT matrix. So first of all, you have to find a column representation of this U. That is U cap is equal to this thing should be here, this thing should be here, this thing should be here, and this thing should be here. Okay, so you have this U, it is a column matrix, that should be multiplied with this script C. This script C can be written as C Kronecker C. So what is C Kronecker C? Kronecker product of C and C. So C 1D C we know. So first of all, you have to make this image to a column matrix. Then you have to find out this script C by finding Kronecker product of C and C. Then just multiply this capital C script C by this U cap. Then you will get one column matrix like this. So since it is 2 by 2, we'll get a 4 by 4 matrix here. So 4 by 4, and here it is 4 by 1. So we'll get a output 4 by 1 matrix like this. That should be converted back to output V matrix like this. So this thing goes here, this thing goes here, this thing goes here, and this thing goes here. So these all are already explained in the last lectures. So question 2 is find 2D DCT of an image A 1 2 3 4 5 6 7 8 9. 1D DCT matrix D of order 3 is given. So how we can find it? So first of all, we have A matrix, image matrix, input matrix A. So that should be converted to a column matrix like 1 2 3 4 5 6 7 8 9. Then we have 1D DCT matrix D. Then from D we have to find out the script D by Kronecker product of D and D, which is equal to, it is a 3 by 3 matrix. So D is a 3 by 3 matrix. So after converting that to script D, we'll get a 9 by 9 matrix. So the output B is, D into A. So after finding this Kronecker product, we will get what? So this D is a 3 by 3 matrix, right? So first element into all the elements. So we'll get one. I am not calculating here. So D will be what? So if we have a D like this 1 2 3 4, and script D will be D Kronecker D is equal to 1 into all the elements. So 1 2 3 4, then 2 into all the elements, 2 4 6 8, 3 into all the elements, 3 6 9 12, 4 into all the elements, 4 8 12 16. This is script D. So like that you have to find out a script D corresponding to this D. Okay, so we'll get a 9 by 9 matrix, and you have a column matrix for A, that is 9 by 1. So we'll get an answer B with the size 9 by 1. So that should be converted back to an image B, a 3 by 3 image. So this is the answer. Then we have a Walsh-Hadamard transform. So its kernels are given like h1. The first one is 1 by root 2 1 1 1 minus 1. Then the higher order WHT transforms kernels will be like the Kronecker product of the lower order transform. So the question is, write the Hadamard matrix of order n equal to 3. So H3 will be H2 Kronecker H1 or H1 Kronecker H2, both are the same. So H1 we have 1 by root 2 1 1 1 minus 1. So this thing becomes 1 by 2 root 2. 1 should be multiplied by all the values. So 1 1 1 1 1 minus 1 1 minus 1 1 1 minus 1 minus 1 1 minus 1 minus 1 1. Then this one should be multiplied by all the values. This thing also multiplied. This one also should be multiplied by all the values. And this minus 1 should be multiplied by all the values. So minus 1 minus 1 minus 1 minus 1 minus 1 1 minus 1 1 minus 1 minus 1 1 1 minus 1 1 1 minus 1. This is the answer. Write the Hadamard matrix of order n equal to 3. Then higher order matrices can also be derived from this H3. Next comes KLT transform. So it is a data dependent transform. And so basis images are data dependent. So if you have any a number of data you have, so from that only we will find the basis images. But in the case of DFT and DCT, basis images are fixed. So you have order n equal to 2, and for n equal to 2 the DFT matrix basis is fixed. So there is no change according to the input data we are giving. But in the case of KLT, it is a data dependent transform. So basis images are calculated from the input data itself, and there is no separability notion like in the case of DFT there is row column decomposition, and it is but here it is not there. And KLT transform is much complex, not fast, but it can be used as a benchmark transform, since it purely diagonalizes the covariance matrices. So so which of the following transform is optimal for the particular kind of data? So a particular kind of data, since the basis images are derived from the data itself, we can say that KLT is the best. Okay, so that is what is meant by optimal. Okay. So the we can use any transform, but the KLT transform is the optimal transform, unlike the case of DCT and DFT. Then comes energy packing efficiency and decorrelation efficiency of a transform. So after transforming, say if we have a covariance matrix like this R, then after transforming that to a transform, like we are finding R dash is equal to U R U Hermitian, where U is the unitary transform that we are using. So after transforming this to R dash, we can find out the energy packing efficiency of the R dash. So R dash is the transformed image. So how we can find out? This R dash can be a matrix like this: A, B, C, then some D, E, etc. Then if we can say that this transformed image is more energy packed, if the energy is concentrated on the this portion, this lower portion of the matrix, then we can say that, like if the energy is concentrated on very less number of coefficient, then we can say that it is more packed, energy is more packed. But the whole energy is distributed across all the values. Like if we have a 10 value here, if you have a value 10 here, and if you have again a value 11 here also, then we can't say that it is more energy is more packed on R dash, because all the values are distributed. But in order to be used for some compression task or something, energy packing efficiency should be very high. So the equation for energy packing efficiency is summation of the diagonal elements value for a particular value of m. So if you have to find out the energy packing efficiency for m equal to 3, you just find the summation of 3 values first divided by the all values. Okay, so if the energy is packed more on the least values, this thing will be higher. So that is the case. Question 5. For the following matrices, which one has larger energy packing efficiency? And we have decorrelation efficiency is also there. Decorrelation efficiency, what does it mean? So we have R dash here. Decorrelation efficiency means the other value should be 0, should be decorrelated. What does that mean? So if we have two these things are also mentioned. We have a data structure like this, so we are converting this basis into another basis such that in the other perpendicular axis the data spread is very less. So that type of transformation is what we want. So R dash should be, the off diagonal element should be 0. That is what is measured by using decorrelation efficiency. So here we are taking the case other than the diagonal elements, I not equal to j case. So question 5 is, for the following matrices, which one has larger energy packing efficiency for m equal to 3? For m equal to 3 is like we have to take the first 3 values. Okay, so by just visual appearance, we can say that this one has energy packing efficiency more, because here the values are more concentrated on the left side, right? But here we can say that it is spread like this. So we can just find energy packing efficiency is summation of the first 3 values. So 25, 19, 13 divided by all the diagonal values, 25 plus 19 plus 13 plus 7 plus 1. So we will get a value 0.8769. But here we will get energy packing efficiency of R2 is 1 plus 7 plus 13 divided by 1 plus 7 plus 13 plus 19 plus 25. So we will get approximately 0.3231. So we can, from numerical answer also, can say that its energy packing efficiency is very high. Which of the following are true for a covariance matrix R? So given options are R equal to R Hermitian, eigenvalues of R are real, and eigenvalues of R are always positive. So which of the following are true? Actually 3 options are correct. So why R is equal to R Hermitian? So normal covariance matrix R can be written as XX Hermitian. So R Hermitian can be written as, which is also XX Hermitian, which is equal to R. So that is the first one. Then we have eigenvalues of R are real. So for that, first take the case of X Hermitian Rx. So this thing, what is our expectation of another y, a particular distribution? Okay, expectation of X thing we can write like this. Then take it as a Z. Then this thing is Z Hermitian. So this thing will be always greater than or equal to 0. So X Hermitian Rx is always greater than or equal to 0. Then for eigenvalues, Rx should be lambda x. So X Hermitian Rx should be lambda x, should be greater than or equal to lambda is a positive, means constant value, right? So lambda X Hermitian x should be greater than or equal to 0. So this thing is always positive. So this thing should be positive. So this is the second one. Eigenvalues are always third one, eigenvalues are always positive. Then we have third one, eigenvalues are real. So we know Rx is equal to lambda x. Rx Hermitian will be lambda star X Hermitian. Lambda is a constant, right? But we have to find the conjugate. So this thing will be X Hermitian R Hermitian is equal to lambda star X Hermitian. R Hermitian equal to R. So X Hermitian R equal to lambda star X Hermitian is multiplied with X here. Then we'll get Rx is lambda x. So X Hermitian lambda x is equal to lambda star X Hermitian x. This thing is lambda X Hermitian x is equal to lambda star X Hermitian x. So lambda minus lambda star is equal to 0. This gives lambda equal to lambda. So conjugate is equal to lambda. So it will give like eigenvalues of R are real. So these are the proofs for these three statements. Then we can go to KLT. So in KLT, how we can find KLT? So KLT is a transform phi. Okay, that can be applied to a input matrix V. So we'll get some transformed output V. But that transform, that phi should diagonalize this covariance matrix R. So this type of case will be obeyed in the case of KLT transform. So the transform phi will be derived from R itself. So from the covariance matrix itself we will derive this phi. That is the trick here. Okay. So how we can find this R? So from a data X, you will have some data. From that you will find the covariance matrix R. Okay, expectation of XX transpose. Then from this R you will find the eigenvectors of R. Then that eigenvectors of R will be what? The columns of phi Hermitian. So that is the case. So first of all, so this is how you will find the phi matrix. So this phi will be, if the input will be of size n, then the phi will be n by n, but we can take only the significant values of eigenvectors. So say you are taking only m significant values, so phi can be written like using m by n matrix. Then we can just multiply that with the input. So so the transformation may not be much accurate, but it is okay, since we are neglecting only the insignificant eigenvectors. Okay, so if you are increasing the number of eigenvectors that you are neglecting, the error will be very high. And the error can be like, if you are taking say you have n equal to 9 eigenvectors are there, and you are taking only n equal to 6 eigenvectors, m equal to 6 eigenvectors, so you are nullifying 3 eigenvectors, right? And you have that eigenvalues corresponding to that eigenvectors that you are neglecting. Then and after that you'll find some v from that input image u. So after reconstruction v back to u cap, you will get some u cap, but that may not be as similar to this initial u. There can be some errors because we are not using the full eigenvectors. Okay, and the error will be equal to the summation of the what eigenvalues. So question 7 is, the eigenvalues of a covariance matrix R of a data x are 3, 2, 5, 7, 10. If you are constructing an input data back using 3 most significant eigenvectors, what would be the square error between x and x? So you have to find out this thing. You have lambdas like we can just write them in descending order. So the error will be summation of this lambda I. So 3 most significant eigenvectors we are using and 2 we are neglecting. So we neglected is 3 and 2. So the error will be 5. Then one simple question, perform KL transform of the following matrix. So the first step is you have to find out covariance of x, like right, R matrix you have to find out first. So R matrix can be written as expectation of XX transpose minus X transpose. Okay, so x bar is the mean. So we have x1 is equal to 4 minus 1, x2 is equal to minus 2, 3. So first of all you have to find out what is the mean of these two vectors. So you will get it as minus 1, 1. Okay, then you can find out this thing, this value. This will be 1, 1, 1, 1. Then you have to find out expectation of XX transpose. So for each x1 and x2 you have to find out x1 and x1 transpose and find the mean. So 1 by 2 into 4 minus 1, 4 minus 1 plus minus 2, 3, minus 2, 3. So we'll get it as 2 minus 1 minus 1, 1. So R matrix will be this thing minus this thing. You will get 1 minus 2 minus 2, 0. Okay, this is your R matrix. Then from that only you will find the eigenvalues. How will you find out eigenvalues of R? R minus lambda equal to 0. Then from that you can find out, right? So how will you find out 1 minus lambda minus 2 minus 2 1 minus lambda, determinant is equal to 0. So after multiplying this to this you will get 1 minus lambda square minus 4 equal to 0. So you will get 2 lambdas. By using 2 lambdas you can find 2 eigenvectors also. So for lambda equal to lambda 1, the first lambda, you can write R minus lambda 1 I into a vector v0 equal to 0. So v0 can be find out from using this equation. So that v0 I'll write eigenvector corresponding to this R is it will be minus 1.28081. Then V1 corresponding to the next eigenvalue will be 0.78081. So after finding this eigenvectors, you can find the transformation matrix, KLT transformation matrix T as V0, V1. Just write it as a 2 by 2 matrix. Okay, then just multiply this with any input image. So you can find it as like this T into 4 1. So that will give the transformation corresponding to that element 4 minus 1. Okay, then for minus 2 3, just find the transformation. So this is how we can find the KL transform. Then comes SPD. So what does SPD do is, you have a matrix like this. You decompose that matrix to A, sigma, B Hermitian, such that when we multiply these three, you should get the input matrix S back. So this can be done using eigenvalues and eigenvectors. So and sigma will be a matrix of singular values. Okay, sigma will be, capital sigma will be matrix of singular values. So we can go through this problem first. Find a singular value decomposition of A 1 minus 2 3 3 2 minus 1. Okay, so first of all you have to find out. So this A should be written as U V Hermitian, U sigma V Hermitian. This U V sigma we have to find out. So first of all find X equal to A transpose A. 10 4 0 4 8 minus 8 0 minus 8 10. Then find the eigenvalues of the matrix X. So you will get 0 10 18. Corresponding to every eigenvalue, find the eigenvectors. V0 you will get minus 1 by 3, minus 2 by 3, 2 by 3. V1 you will get 2 by root 5, 0, 1 by root 5. V2 you will get minus 2 by 3 root 5, root 5 by 3, 4 by 3 root 5. Then singular value matrix sigma can be written as square root of this lambda. So 0, root 10. Sorry, first of all you have to make them in descending order. Okay. So these three matrices will come where, in the case of V, this V. Okay, for finding U, you have to first find Y equal to A transpose like this. Then you have to find out its lambda and its eigen vectors. So after finding eigenvectors, you have to normalize all the eigenvectors. So you can write this A as so after finding this U, you will get it as 1 by root 2 minus 1 by root 2. Root 18 0 0 is sigma. Then you have these three elements written like this. Okay, so after multiplying this, you should get back this capital A. So these all are the topics. So about lab assignment 8, you have to construct a matrix R of Markov process. So for that, row is given in the question. So from row you can find R, then you can write a Hadamard matrix of order 8 by 8, and I think one is missing here, Hadamard matrix, and C is also you can find out, cosine DCT matrix also you have to find out. So you have R, H and C. So you have R matrix, H matrix and C matrix. So transform R using H and C. So you have to find out HR H transpose and CR C transpose. So those are this thing and this thing. Then you have to find out the energy packing efficiency and equivalent efficiency of these two transformed matrices. Then you have to construct a beta square R inverse. So that thing should be like a tridiagonal structure. Then you have to just construct a purely tridiagonal matrix Q, then diagonalize both using DCT matrix. So you can verify that DCT matrix can purely diagonalize Q matrix, but for B that there is diagonalization, but it is not that accurate as in the case of Q matrix. Then the next question is, given a matrix G of size 8 by 8, you have to find out okay, in the question it is not given. Okay, so did you submit the answers? Okay, did you submit the answers like for okay, wait a minute. Okay, it is size of 8 by 8, right? Okay, so can you try with means just first you try with m equal to 5, then you submit it. I think for every m, I'm not sure whether it accepts or not the code back. Like for m equal to from m equal to 5 you try, okay, and submit. If you have any issue you can ask there. Okay, so that's all about this last week's videos. So do you have any doubts? And you could submit that blur thing, no? Okay. Solution. So did you do that? Did you submit it? A52. assignment mentioned to use only 1D DFT. Is it in the question or in the IPVNB file? The collab file or in the PDF itself? It is mentioned like to use 1D DFT. Okay. So which one did you use? I-52. One D F50. Then how did you convert that to image? Okay. Whether there is any problem like did you get the output? Okay, I think there will not be any problem. Actually, question part I'm not dealing with that. That is why. Okay. So from forum did you get? Oh, okay. Okay, I'll also check. Okay, this thing I'll ask them. Okay. And did you register for exam? Versus why F50 and IF50? Which one should I read? Combined 4. Okay, is it there in the forum? Okay, from that I'll read. Okay, I got the question. I'll go through it. Okay, and if you have any doubts, you can just send on this email ID. Okay, and okay, codes and all you send this email ID you can use. This is my email ID. And in forum try to avoid that code lines and all, because everyone will see that, right? So everyone has to submit assignment, so your code might be used by others. Okay, anything else? uh, is it not visible? Okay. Did you get the email ID? Okay, okay. Then we can wind up. Okay, thank you.